if you look at medicine as a discipline, it's inherently multimodal in nature. Doctors and clinicians routinely interpret data from all sorts of modalities, ranging from clinical text to imaging to lab records and lab tests and vital signs and census data. We like to set the bar high, and we like to go after the most ambitious problem. And for that, the most ambitious version of the problem felt like building a generalist biomedical AI agent. It's no longer science fiction to think that that is possible.
Hello, and welcome to The Cognitive Revolution, where we interview visionary researchers, entrepreneurs, and builders working on the frontier of artificial intelligence. Each week, we'll explore their revolutionary ideas, and together we'll build a picture of how AI technology will transform work, life, and society in the coming years. I'm Nathan Lebenz, joined by my co-host, Eric Torenberg. Hello, and welcome back to The Cognitive Revolution. I am super excited about today's conversation about Google's new multimodal Med-PaLM model with returning guest Vivek Natarajan and lead co-author Tao 2. This paper, published just a few months after Vivek was here to discuss Med-PaLM 2, extends Google's insane run in generalist medical AI by training a single system that accepts not just clinical text, but a wide range of medical imaging and even genomics data, and trains it to perform 14 distinct medical tasks, of which text-only medical question answering is just one. The headline from this work is that this single model sets new state-of-the-art performance records across a number of tasks, while also coming close in a few more, all with a single set of model weights. For radiology report generation specifically, the AI output was preferred to that of a human radiologist more than 40% of the time. The promise for society over the next couple of years is no less than an AI doctor in everyone's pocket all around the world, one that can not only understand patient language and images, but also incorporate and interpret new things like genomic data in superhuman ways. The insights from this conversation were, for me, many. I talked with Vivek and Tao about how predictable such incredible progress has recently become, the many different tricks and best practices that go into training a large-scale model like this, how quickly and efficiently they can conduct this work as they stand on the shoulders of giants at Google, the extremely promising generalization that this system is already showing, how much low-hanging fruit remains available to improve future models' performance, how Google's strategy of building comparatively narrow specialist systems drives value while also promoting safety, the path to clinical testing and deployment of generalist medical AIs, and lots more along the way as well. If you've got any doubts about AI having major impact on humanity over the next few years, I think that after listening to this conversation and considering not just where we are today, but how consistently we are moving forward and how much room we clearly have left to run, I think that those doubts will pretty quickly fade away. As always, if you're finding value in the show, we would appreciate it if you'd share it with friends and post a review to Apple Podcasts, Spotify, or YouTube. And of course, I always love to hear from listeners. This last week, I got LinkedIn notes from a London-based growth equity investor who said that he listens to the show in order to better understand the edges of AI leaders' understanding of AI systems. And also from an intelligent automation leader at an iconic American manufacturing company with over 50,000 employees, who said that he'd watched the AI scouting report on YouTube multiple times. It is both energizing and enlightening to hear why people listen and learn what they value about the show. So please, don't hesitate to reach out via email at tcr@turpentine.co, or you can DM me on the social media platform of your choice. Now, on to the show with Vivek Natarajan and Tao 2, authors of Google's new multimodal Med-PaLM. Vivek Natarajan and Tao 2 from Google, authors of Multimodal Med-PaLM. Welcome to the Cognitive Revolution.
Pleasure to be back over here, Nathan, and I'm looking forward to this one with Tao.
Yeah, same, excited. My first time doing a podcast.
Well, I take pride in having a lot of first-time podcast guests who are doing great work on the show. So welcome to a proud tradition for me. You guys have been really on a tear at Google of late with an incredible series of papers specifically focused on the medical use case with Med-PaLM, Med-PaLM 2, and now multimodal Med-PaLM. And it hasn't even been that long since our first episode. Just a few months have passed between when it was like, okay, we sort of achieved with Med-PaLM, maybe whatever, 6 to 8 months ago, we achieved kind of passing level on the, licensing exam, to with Med-PaLM 2, oh, we achieved expert level question answering. And now with multimodal, you are incorporating all these other types of data, imagery, and even genetic information. So it's really just incredible how fast this is moving. And yet at the same time, like, I kind of wasn't even super surprised by it, because it just feels like you're on such a consistent roll at this point that these things that were once unthinkable are now almost expected. For starters, like, tell me what is that like? Like, you're working at this kind of critical point, I feel like, in human history, and all these milestones just keep falling one after another.
Yeah, I think the key over here is we have been building on the shoulder of giants over here at Google. And so in many ways, all this started off with the transformer revolution back in 2017. And then more recently with the PaLM series of work and the underlying infrastructure that allows you to train large models effectively and efficiently at scale. So I think that helps a lot. And then the second thing is, at least on the medical AI side, again, my team at Google, we've been around for several years now, and we've had quite a few successes, but also a lot of failures, and we've learned from that. What helps is we also have like a very nice and strong interdisciplinary team that really understands medicine and healthcare. And so that in turn helps us, motivate and frame problems in an appropriate manner and then go after them. And so I would say this is just in many ways, the foundations have been there and around for a long period of time, and this just feels like surfing the wave. Like, it's just the right place at the right time, given all the foundations that exist, and we're just incredibly lucky and fortunate to be part of it.
So let's characterize this system a little bit, starting with the inputs, I suppose, probably the natural place to start. Previous systems have been all text. This system accepts a lot more different kinds of inputs. So tell us about the new types of inputs that it accepts and how you selected them.
I think the motivation for this is fairly clear. If you look at medicine as a discipline, it's inherently multimodal in nature. Doctors and clinicians routinely interpret data from all sorts of modalities, ranging from clinical text to imaging, to lab records and lab tests and vital signs and census data. So doctors and human clinicians are remarkably proficient at doing that, and I would say that that is required to like really understand the context of a patient, the context of the healthcare system as well, and that in turn helps you provide care more effectively. So if we want to be using AI in such scenarios and such situations, then these models do need to be multimodal in nature. And that's what we are building towards. And now, how exactly do you do this? How do you make large language models multimodal? I think there are a variety of approaches where I think the trade-offs are like, how much data do you have? How much compute do you have? And I think many people have proposed a lot of different ideas. But for us, I think in many ways, we like to set the bar high, and we like to go after the most ambitious problem. And for that, the most ambitious version of the problem felt like building a generalist biomedical AI agent that, just with the same set of model weights, the same set of parameters, can solve a bunch of different biomedical tasks, can encode and interpret a bunch of different biomedical modalities. And so this has been something that has not been previously done before. People have shown the concept of a generalist agent in other domains. DeepMind famously, I think a couple of years back, showcased Gato, which had, I think, 600 different tasks spanning a variety of modalities, actions, observations, and beyond. And they showed that the same model could not only chat with you, caption your images, but also be used as the policy model for a robot that stacks blocks, the policy model for an agent that plays Atari games. And so that was impressive. But I think there are unique challenges in medicine just because of the nature of the data and the nature of modalities that you're dealing with. And so in that sense, while there was precedence, and again, we built on top of another system known as PaLM-E, which was more recent, but very similar in flavor to Gato. The fact that there are unique challenges inherent in medicine and biomedical data. So that was, I would say, the uncertainty associated with this.
Yeah, I think to answer your question directly, we included data from dermatology, pathology, chest X-ray, mammography, and also genomics, in addition to clinical text. All the modalities converted into an image that is digested by the model.
Most of those images, I have like a reasonable, intuition for what they are, right? I can picture, and I assume listeners can picture an X-ray, and can probably, we did an episode actually about virtual tissue staining, which was fascinating. And if anybody heard that, then they certainly should have a memory of kind of what a pathology image from a tissue on a slide under a microscope would look like. As I was going through this, I didn't have an intuition though for the genomic data. There sounds like there's a little bit of kind of a trick or something, maybe it's standard in the field, but I wasn't familiar with representing genomic data in image form, and kind of had no intuition for how that would work.
Yeah, so we had brilliant collaborators from the genomics teams at Google. So they have developed deep variant model, which is the state-of-the-art variant calling model used in the field. So what they did is they converted in the genomic sequence into a 3D tensor that can be digested by inception type of vision network. So we borrowed the idea from their model, and then we did some reshaping in order to make the image compatible with our vision transformer encoder.
In our team, I think dating back to again 2018, 2019, the genomics Google Health team has been building out the system known as deep variant that's used for variant calling. The way they did this was actually cast that problem into an image classification problem, because back then that's what deep learning models were really good at. We were very good at like computer vision, and I think LLMs did not just yet catch up. And so the first version of these models used inception systems and later on resonance as well. And so this clever encoding of genomic signals and data in the form of like image representations helped with that task. And the models were actually really, really good. And so if you look at the performance of these systems, they are really accurate. And so the FDA runs a challenge known as Precision FDA Challenge. And I think for a couple of years, I may not be getting the details right, but this system won the challenge. And maybe another bit of detail over here is more recently, so there was this effort from a bunch of researchers at Stanford led by Professor Yuan Ashley. And they had this system that set a world record for sequencing variants and calling out what might lead to a particular disease, and they set the world record for that. And so one of the key components in that system, in addition to all the innovations that's been in general going around, like really fast real-time sequencing, has been this variant calling system that really helps in improving the accuracy of the reads that you have. And so that was like something that was celebrated. I think it was published in the New England Journal of Medicine. And so this component, this variant calling system, was a key part of that.
If I understand correctly, then it's genomic data that is encoded in an image, and then the output of that is like a sort of, I guess it was more of a classification originally, like this is a unusual sequence, or this is a sequence that is likely to be problematic because it's unusual. But now you guys are doing that in a much more holistic way, right? Like now it's not just a classification scheme. So did you essentially recreate that capability in the course of this PaLM fine-tuning? There, you didn't like actually bring any weights or anything, right, from that prior work?
Yeah, that is correct. So all this was trained from scratch, in addition to all the other tasks that we had in medical imaging and doing medical question answering from text and beyond. I think one of the nice things about the generative setup that we have with large language models is everything can then be framed as a generative task. And so even classification problems, which were previously, you were outputting a vector encoding probabilities of different classifications. Now you can just have a language model and say, well, I think this is a suspected variant, or I think this is like this disease in dermatology or whatever. So it just unifies everything and provides language as a common grounding. And we can get into this in more detail, but that gives you a lot of advantages.
We didn't really build on any previous specialized model weights. So what we did actually build on was the weights from the PaLM-E model, which is the backbone of vision language foundation generalist model that was originally designed for robotic tasks.
Yeah, and maybe very quickly to add to that, that did not have any medical domain fine-tuning. So it did not see any dermatology images or these genomic variant images and any medical text. And so when we looked at the out-of-the-box performance, and that was one of the baselines that we compared to as a generalist model without any medical domain fine-tuning, the model was not very good at all. And so that in turn shows the importance of medical domain fine-tuning, medical data, and medical specialization if you want these kind of systems.
Yeah, that's super interesting. So PaLM-E, it was basically to help robots move around the kitchen and like pick up, objects and follow directions, right? So yeah, it's amazing how all this stuff is kind of just, I don't want to say easy to recombine, but I want to hear a little bit more about this, your kind of successes and maybe some failures too, because just the pace at which you guys are coming out with these results, it feels to me from the outside like everything's working.
Hey, we'll continue our interview in a moment after a word from our sponsors. If you're a startup founder or executive running a growing business, you know that as you scale, your systems break down and the cracks start to show. If this resonates with you, there are 3 numbers you need to know: 36,000, 25, and 1. 36,000. That's the number of businesses which have upgraded to Netsuite by Oracle. Netsuite is the #1 cloud financial system, streamline accounting, financial management, inventory, HR, and more. 25. Netsuite turns 25 this year. That's 25 years of helping businesses do more with less, close their books in days, not weeks, and drive down costs. 1, because your business is one of a kind, so you get a customized solution for all your KPIs in one efficient system with one source of truth. Manage risk, get reliable forecasts, and improve margins. Everything you need all in one place. Right now, download NetSuite's popular KPI checklist, designed to give you consistently excellent performance, absolutely free, at netsuite.com/cognitive. That's netsuite.com/cognitive to get your own KPI checklist. netsuite.com/cognitive. Omneky uses generative AI to enable you to launch hundreds of thousands of ad iterations that actually work, customized across all platforms with a click of a button. I believe in Omneky so much that I invested in it, and I recommend you use it too. Use CogRev to get a 10% discount.
And, that probably isn't quite literally true, but when you set out to do this project a few months ago, were you guys pretty confident that this was going to work and get basically here? Or did you actually have, doubt in your heart of hearts that, hey, maybe this still won't work? I would have been betting. I think if I was you, I would have been betting on it working pretty well. But I'm wondering, if there's actually more uncertainty in what is possible, when you're in the trenches doing the work.
I think at a high level, you are right. The fact that, systems such as Gato and Palmy and Flamingo and various others existed pointed us that this thing is doable. But I think it always comes down to the details, and the devil is in the details. The other question is, okay, from a scientific perspective, it is interesting to build a generalist agent that can, broadly be competent at a bunch of different tasks. But then the other question is, okay, if you're looking forward, what is the utility of this? And today we have a lot of specialist systems. For example, there's a highly accurate, mammography breast cancer screening system that's being used in clinical trials across the world. And so if you want to use this generalist agent, you need to be able to perform at that same level. And so that's kind of the key question. Okay, from a scientific perspective, it's interesting, but you also have to think about the utility. And so that was the other question that we were trying to answer. So can we, make this generalist agent perform at the same level as these narrow specialist models that you have, which have been really customized and fine-tuned with a lot of effort, with a lot of compute, with a lot of brain power, and make it reach the same level of performance. And then the second thing is, the other hypothesis is as you start training these generalist agents to encode a lot of different biomedical data at scale, can you see interesting phenomena such as positive trust transfer or combinatorial generalization that emerges as you use language as a common grounding to interpret different modalities and solve different tasks? Can you do more effective few-shot learning? Can you do more effective multimodal reasoning? And so I think those are the other things that we were hoping we would see. But then one of the difficulties with AI systems, especially at this scale, is, you may have hypotheses, but then you have to build out these systems first. And that often takes a lot of compute. And again, Tao can tell you more about all the details that went into it, all the knobs that he had to tune to make the system really work. And so, and if you get some of these details wrong, then you won't get what you expect. And so that's maybe where always the challenge and the uncertainty is.
Yeah, I think for us, it's a continuous learning process, even now when the paper is out. Like Vivek mentioned, there are different options of the foundation model choices for a biomedical generalist model. For example, PaLM and also PaLM, which is also by a large foundation model, vision language model by Google. I think the choice of model kind of also depends on what the data set we have, and importantly, what kind of tasks that we want the model to perform. So there are some pros and cons to different model architectures, and maybe we can come back to that later. So I think one thing that I do want to highlight is, so for the Med-PaLM, we did not really fine-tune the model with multiple images during training. I think this is something certainly is important for a lot of biomedical applications, especially if you want to look at a longitudinal change.
Yeah, and maybe just to add a quick detail over there is the reason for doing that is mostly compute reasons, because if you have multiple images, then you have to encode them and get the representations, and so that adds a little bit more compute. And so if you can teach the model the notion of like an image without actually giving it a real image, then that just makes it practically more efficient to train. And so we decided to use that regime. And then if you look into the paper, we show that that is actually quite effective. And so even if you don't give the model an actual image, but then just use these tags for an image in the few shot instruction, that is still useful enough for the model to understand the context. And in turn, the model can generalize to scenarios where you start giving the model actually multiple images, such as multiple views of a chest X-ray, multiple views of a mammogram, or like previous cases of your radiology images or whatever. And so that was one of the tricks again that we used. And so ultimately, I think these days, in many ways, training large language models, foundation models, multimodal models, it just comes down to assembling a reasonable bag of tricks and putting them together in such a manner that you're not using a whole lot of compute, and based on the data you can end up building like a system that's hopefully well optimized for a task that you want to be solving and you care about. So there's not a lot of, I would say, secret new knowledge. It's all about like putting these tricks together in the right way, in the right format, and then once you start putting all of them, and they start accumulating, and that leads to these outsized improvements. And I think that's true for not just this work, but also PaLM, PaLM, and also for other systems outside GPT-4. I think people who build that, they'll also tell you the same set of things.
Yeah, there's certainly a lot of know-how, that seems to accumulate in these leading organizations, and certainly, for the this is not really the topic of today's conversation, but if one is looking for moats, the incredible know-how that the team has that applies all these little detailed, nuanced tricks in the effective way, is a pretty good place to look. Tell me about the team, actually, because there's 50 or so authors on this paper, and I believe the two of you are the first and the last name listed in the author role. How does the team, take me through the whole thing, maybe? Like, how does a project like this at Google get decided upon in the first place? Like, how does a team get assembled? Presumably, this is not like a specific unit of hierarchy within Google. I imagine it must, cross all sorts of organizational lines and different kinds of expertise. So I'd love to hear how you kind of bring a team like this together, and what the roles are and who manages it, because it sounds pretty complicated.
I think one of the nice things about working at Google is the fact that in many ways organizational boundaries and hierarchies do not exist. So again, there was no like real top-down mandate that you have to do this. It's more like a bunch of researchers getting together and feeling that, oh, this is tractable and possible, and we should do this. And then the right set of people with the right expertise just coming together, working together for a period of time with intensity, with like a collective spirit, and then that happens. And then the other thing is, again, when you want to do these things the right way, especially in the medical domain, there's a lot of details, say, around data set access, around policy and legal. And typically when you're writing these papers, you tend to ignore those contributions when you're considering who should be a paper author and who should be not. But we don't believe that. We believe that that's also an important part of doing things the right way, and the contributions of, say, people who are providing program management support or product management support are equally as important as the machine learning researchers and engineers and the clinicians who are helping frame the problem and build out the systems. And so in that sense, when you want to do things the right way, where you want to ensure that the data sets that you're using, you have the right licenses to it, there's no like copyright violations, and you can use them onward and so on and so forth, quickly requires a village to start doing these things the right way. And so that is what we try to ensure and stress. And so in some ways, I mean, ensuring that people are acknowledged and included in papers is the least we can do, because that work is equally important. Yeah, I think that is why you see like papers with a lot of authors, because it's really a cross-functional effort, especially when it comes to medicine. And then the other thing is, again, we are not doing this in vacuum. We are not training these models from scratch, but rather we are building on top of like the authors of PaLM and PaLM-E. So for example, you can see Pete Florence and Danny and Akansha Chowdhury on this paper, and they've been like incredible sources of support for us, bouncing off ideas, telling us what to do, what not to do. And they all care about the medical domain, but maybe they don't have the time to like push deeply on this. And so it ends up being a very nice collaboration. And so that's why you see a big author list, basically.
Yeah, one thing I want to add to that is we also receive tremendous amount of help from our in-house clinicians, which is critical to do any biomedical applications, because we need fast and accurate feedback for us to be able to do model iterations and give us directions. I think in the Med-PaLM in particular, we are working with radiologist Chuck. So he have been providing tremendous insights on the model generated readings on the chest X-ray images. I think we use him as a successful metric, like his input.
Yeah, maybe another quick detail is actually Chuck helped craft the prompt for the chest X-ray task, and so if you look at it, it's very detailed and it's like crafted as if how a radiologist would actually interpret an image, like look at different parts, how you collate the findings and summarize the findings, and how what you should look for, and so it's very detailed. The nice thing is we have models today that can follow such language instructions to a high degree of accuracy. And the other thing is we have clinicians who can then help us craft these instructions and provide the human intuition in language form. And so, yeah, that's just the best of both worlds bringing together and helping push things along over here. And maybe the final thing I would add is the incentives are also different over here. Like it's not a zero sum game anymore. And also science as an endeavor, especially in AI, the way it has evolved, it's no longer, I think, an individual doing brilliant things like say Einstein did in physics like 100 years back, but rather like groups of people coming together and building awesome stuff. And the more we are able to empower groups of people to come together and build things fast but also effectively, I think the better it is. And and ensuring that that the mechanisms for that exist is great. And I think in many ways, I think DeepMind and OpenAI, they set the standard over here for that. And we just hope to replicate, because I think that's going to be the future for AI. And so there's no need to play zero sum games over here. We can be, very generous with inclusion and authorships. And so that's, I think, one of the benefits of being in industry, say, versus in academia, where that's a little bit more challenging.
So the breakdown is like, it's kind of everybody that's involved in all these roles. So you've got like literal doctors that are also Google employees that are providing the expertise. You've got legal, that's handling all the kind of licensing and whatnot, as you said. You've got infrastructure engineers. You've got, potentially people that focus specifically on like data set preparation. How many at the end of the, once all these other roles are carved out, how many down the fairway ML researchers are on this project?
It's hard to put a number exactly on that. I would say it's probably 8 or 10 maybe who have like strong and deep ML expertise. But also one of the nice things is we have people who are fluid. And so like someone who, for example, is doing infrastructure is not only doing that work, but they also tend to be equally competent at training models and building models at scale. So the roles are kind of fluid in that sense. Like once people come onto the project, they'll just do everything that it takes to make it succeed.
Yeah, and also one detail that so compute is always like a resource, so not multiple people can run the experiments simultaneously.
So that's something you have to plan ahead of time, especially when you're training the bigger models.
This pathways framework, right? This is when people talk about PaLM, the P in PaLM stands for pathways. And I don't really know what that is. If I took my best guess, it would be like, it sounds like it's a framework for tapping into compute. Google has its own chip, the TPU, which is kind of an alternative and proprietary AI focused chip, as I understand it, that's not, doesn't do all the graphic stuff, but is specifically optimized for AI workloads. What is pathways, and tell us about the process of compute. Like from the outside, one would maybe imagine that like compute is effectively unlimited at Google, or at least for projects like this, but it sounds like maybe not so simple as that.
I think Pathways was kind of like Jeff Dean's dream and vision, and many others have worked on it, including Akansha, who's a co-author on this paper. At a high level, it's a large-scale ML orchestration system that allows you to train giant multitask multimodal models on thousands of accelerator chips, which in Google's case more often than not turns out to be TPUs that are optimized for this. We could probably spend like another full episode talking about Pathways and the magic behind it and the infrastructure and everything that goes into it. But I think at a high level, what is happening is if you look at large language models today, they have this transformer base, and transformers are mostly a lot of matrix multiplications, matmults, and the combination of JAX XLA, which is short for accelerated linear algebra. It's a compiler that allows you to port code written in JAX to multiple different accelerators and distribute the code across them. And that with TPUs that are optimized for AI workloads, it turns out to be like really, really magical because they're really, really optimized for doing the computations effectively and also the communications that you need to be able to do when you're training these systems at scale. And when I say communications, it means splitting out the models, passing along activations and gradients between them, and so on and so forth. And so that system as a whole is really, really well optimized. We can go into a lot of details of what makes JAX really, really special as well from a developer perspective. Like, for example, the NumPy interface that allows you to hack things at a low level, or stuff like autograd and just-in-time compilation that we have, or auto vectorization, all those sorts of features that make JAX really a really good system. But like if you were to just zoom out and look at it from a high level, it's just the effectiveness of that framework and the co-optimization with the hardware that allows you to train these transformer models really, really effective at scale with the kind of compute that you have access to at Google.
We did an episode with a couple guys from Mosaic ML not too long ago, and they've got a lot of different things to bring to the table. But one big value driver of that company is, hey, we give you a really high level, abstracted way to think about defining what it is you want to do with a data set and an optimization target, and then you can kind of hit run, and all the stuff below that of coordinating the different devices and making sure that the data flows as it needs to flow, you really don't have to worry about that. And obviously, that company's had a good outcome since the time that we had that episode. So it sounds like Pathways is basically the internal Google version of that, such that today, and this is like, very, I get why you're saying standing on the shoulders of giants, because if you had to do that every time, obviously you'd be probably 100 times longer in delivering a project like this. But it sounds like you get to work at a pretty high level. If I understood correctly, it even sounds like it's hardware versatile or agnostic as well, right? Like it could be TPUs, but it could be something else, and you don't even have to worry about that from the high level.
Yeah, that is right. I think that's where the flexibility of JAX kind of helps. So you can, work using this JAX NumPy interface that gives you low-level hackability, but then you can also zoom out and use, depending on the project and the choice that you make, like with Flax or PAX, which is more optimized for using this pathway systems and for architecting models and annotating them such that the model can be, with effective model and data parallelism, be effectively mapped onto the physical hardware that you have for training. So there's all these layers of abstraction that you can work with, and more often than not, because of how the system has been architected, you don't have to worry about these details. Especially for me and Tao and others, we were working on this. We are more in the applications realm, in the product realm. But then sometimes when you are training these models at scale, you would, for example, run into spikes and losses, or you may run into non-determinism or stuff like that, where, for example, you need to maybe able to be zoom in and be able to rerun certain steps, and you want to have determinism for that. Or you may want to, for example, ensure that the data set, the batches that you're using, they're all deterministically shuffled so that you can recreate that checkpoint and stuff like that helps with debuggability. So all those features exist. But then again, the nice part about this being a collaboration is we can very quickly, for example, ask Akansha, who's been doing this for several years now, about all these details, and that helps us move really, really fast.
It sounds like the actual project here might not even be like that many lines of code. Like the core sort of model training loop is maybe able to be somewhat simple. Dare I imagine it might even be elegant if you are kind of, you've got obviously giant data set that you had to assemble, a lot of work there. You've got this tower of computing management that, already exists. And then you're kind of bringing those together. Am I right on this, that it's actually not maybe that much code that kind of pulls together a giant data set and a giant pool of compute now that all those pieces are in place?
We train the model on each single task individually, with the uncertainty that we don't know if we are mixing all these things together, it would maintain the performance that we get from training them separately. So we started out doing a lot of experiment on each task individually, and also figuring out the best setup. I think Vivek mentioned that we use this text-only one-shot exemplar as a way of giving the instruction and an example for the model to know how it should craft its response. So there's a lot of experiments to be done on each different data sets. We also tried different setup in our task mixture. For example, for the chest X-ray generation task, we have Chuck providing us very detailed instructions on how the model should write the report. But for other simpler tasks, for example, classification on the mammography, we didn't have that. So I would say it's a lot of trial and errors. And when you're actually putting all these things together, the immediate question that we encounter is how do we address the proportion of each task? So because the data set varies in sizes, if the model only sees the majority of, let's say, chest X-ray, would that be very biased towards this grayscale image? That probably would degrade the task performance on the genomic images. So there are a lot of design choices and experiments that we have to run to tune these hyperparameters. And also from a computational stability point of view, there's something we also encountered in practice, even though this system is fairly mature. But when we assemble all everything together, we encountered gradient instability. So we have to apply some clever tricks to stabilize the gradient for the model to be trained properly.
Yeah, so maybe just to summarize, perhaps the number of significant lines of code is not that big, and given especially we have existing models that we can fork off and build over here, and the infrastructure is already fairly robust. But then getting the model to actually train and behave well, and the number of choices that Tao highlighted, and I think that's still a very small compared to the actual number of details that we had to go through over here. Yeah, the number of experiments that we had to run and manage to get these details right, and then transfer that over to when you're training up, say, the 64 or the 84 billion model or the 562 billion model that you have. That is, I think, where the bulk of the work is. And then the other big part of the project is obviously the human evaluation, setting up the infrastructure for that, the user interface for that, and doing all the studies around that is where I think the other area where a lot of coding and software engineering comes into the picture, in addition to the clinician inputs and everything.
Yeah, so the model behaves kind of different when it's small scale versus large scale. I think when I look back on the experimental log, I think I ran 300 experiments in the past 4 months to do this paper.
So in practice, as you're doing this, there's 3 model sizes that are reported on in the paper. And I think it's interesting to note also that these parameters are kind of now being summed. As I'm reading through, I'm like, okay, we got the PaLM 8B, and then there's the VIT 4B. VIT is the vision model. So those come together and they become PaLM E 12B. And I do find it pretty interesting. I don't want to overinterpret something like this, but the fact that these parameters are now just being kind of summed, even though it was a language model and a vision model, and now they just kind of merge, and now they're all, working together. I mean, it's amazing how well these things kind of snap together, in all kinds of reconfigurations. But when you're doing this in practice, are you starting with the 8 plus 4 equals 12B model? And, that's where your 300 experiments are running. You're like, I'm going to kind of set up. So if I'm taking myself through I imagine this was a 6-month project. You kind of start off by saying, I'm going to take this, we got to get the data set obviously together. And we already have this, giant compute management stack that I can build on top of. But the first thing we got to do is take a small one, run one task at a time, make sure it's working, tune some hyperparameters. What's the learning rate? Where are these instabilities coming in? Iron out those kinds of details. Okay, now each individual task seems like it's working. Now let's try, running multiple tasks. Let's experiment with the mix, and on you go. And this does seem to be one of the huge things that has also proven to be pretty general, is the idea that you can generalize. I mean, it's you can't fully generalize, right? I find that I always go back to the GPT-4 technical report on this, because they show that insanely smooth curve that predicts the loss of systems as they grow. And, they ultimately predict GPT-4 loss, I think, with the biggest model used to predict it being only 1/10,000th the size of the final GPT-4 model. And so, the loss becomes like incredibly predictable, which is insane how smooth those curves sometimes are. But then you do still have this kind of, but so what, kind of question, like, what is that actually going to translate to in terms of behavior? We can maybe say what we think the loss is going to be, and we might even be right. But does that mean it's going to, be able to do these kind of generalizations that, we kind of hope for, but don't really know? So tell me a little bit more about that story. I mean, fill in some more of the gaps as to what your researcher experience is like beyond what I just imagined.
What you outlined is spot on for text-only large language models. In the sense that from lower sizes of models, you can start predicting to a pretty high degree of accuracy what the loss would be for a large model. But then as soon as you start going into multimodal realms where you're trying to bring in different building blocks together that have been optimized separately, and now you're trying to fuse them together, then I think that becomes far more challenging. You lose some of that predictive power. And it also happens that depending on the data sets that you're training on, how you scale up these components together matter. And right now we're only dealing with vision and language, but you can in the future imagine so many more different modalities that will have their specialist encoders. So if there is, say, some amount of mismatch in the capacity, and it is true that in both PaLM-E and in Med-PaLM there is actually a giant mismatch, especially as we scale up the models. And that's why I would say we don't see the expected gains in performance on some tasks that you might expect, because the language capacity has been scaled in a very disproportionate manner to the vision capacity. And so the vision in turn ends up being a bottleneck, and that in turn limits the overall model performance on some of these tasks. So I would say that's maybe one of the challenges that you encounter as soon as you start going into multimodal realms. Things become much more uncertain. Then you're trying to okay, the only way out of this is actually just to experiment and see what happens.
There are multiple components in the multimodal system: the vision encoder, the language model, but most importantly, there's alignment layer. This alignment layer projects the image token into the same space as language. That's why PaLM-E has this flexibility to construct these multimodal sentences that is interleaved text and image tokens, and can be processed uniformly by the language decoder. So when we think about scaling on some of the classification tasks where the language capacity is not really needed much, I think we didn't really observe a gain when we scale up the language model. And also another source of variability is this vision encoder, vision transformer, was pre-trained on natural images. So they have not really seen much medical image, which has a complete different distribution than the natural images during the training. So the transfer learning on the vision encoder can also result in the bottleneck from the vision side. So I think to properly study the effect of scaling, we kind of need to isolate each component separately. And that requires a lot more like large-scale medical data, because we first need to demonstrate that we can actually adapt the vision encoder to medical domain well before we even connect it into the language model. So I think a lot of things you can only know after you do the experiments. So it's really hard to predict and borrow the knowledge that we have gained from the language model domain, because for language model, even though you are switching from medicine to law, the text token is still in the same domain. It's just a different context.
So there's a number of fascinating things there. One, just to make sure everybody's clear on the results, going through the paper, I was definitely struck by this, that the mids, there's three tiers, right, of model. There's the 12B, the 84B, and the 562B. And one would naturally expect that the 562 would be, the best because it's the biggest. But in reality, it wasn't really so clear. It seemed like it was kind of more or less even between the middle size and the largest size. And if I understand correctly what you're saying, the understanding of that result is that vision model, because across the two, the medium and the large, the language part of the model, the PaLM part got bigger, but the VIT part did not get bigger because the biggest one there is the 22B. So the idea is that if you're basically limited by the power of that, not only because of its just general size, but maybe even more to the point that it didn't have much in the way of medical content in its pre-training. So you're kind of starting from something where it had basically very limited knowledge on that side of the overall system.
Yeah, so that is correct. And that ends up being the bottlenecks. And so a good example of these, like the bottleneck over here, is in the classification tasks, where the output for the language model is something very simple, like saying, for example, oh, this dermatology image has evidence of eczema, for example. So the space of tokens that the model needs to generate is fairly limited. And so there's not much scope for language understanding and reasoning. But then to really do this task really well, you have to understand the image, look at patches and signs and pathologies of different presentations of diseases. And that in turn requires a very powerful vision encoder. And so that is why this ends up being a model, like, say, if the model is too small or it's not been trained properly or has not seen enough medical domain data. And so those are the tasks where you see, the gap really becomes small between, say, the 84B model and the 562B model.
Yeah, and also a practical constraint in training all the tasks simultaneously is all the input image needs to be in the same shape. That certainly creates some bottleneck for the chest X-ray report generation, because the image size that we feed into the model is fairly small compared to most of the state-of-the-art chest X-ray report generation specialized model that they would use.
These are all details that matter. And so in the end, I think that what we have shown so far that is why we call this a proof of concept. But I think there are all these little knobs that you can tune, and we know how to tune them, that I think is significantly going to improve the performance of the system. So hopefully the next iterations, as we have over here, where we can, for example, adaptively, process images at different scales with different resolutions, change the number of tokens that you have for the different modalities. That's going to make a lot of difference, in addition to just purely improving the language model capacity and the vision capacity and bringing in more data.
Yeah, it sounds like we're not at the end of the paradigm just yet by a long shot. How, just roughly speaking, how much data and how much compute are we talking here? I mean, I've kind of looked at the range of fine tuning relative to base model, and these days that range is pretty huge. Where on the very low end, a few dozen examples can kind of fine tune your. It's almost like you get down to few shot territory, right? There's a spectrum from few shot up to pre-training, and you can be fine tuning in a pretty wide, several orders of magnitude, are kind of in that fine tuning bucket. So is this something where it was 1%, more compute relative to, all that had already been poured into the models that you started with, or 10% more compute relative to the base? How do you think about the relative compute investment?
So there are two things. One thing is purely in terms of the number of tokens that you have, and I'm clubbing in image tokens with text tokens. I would say that's not a lot. In aggregate across the benchmark, the number of samples that we had was roughly in the order of 1 million. And then if you were to take on average maybe 10, 20 tokens per sample, then you're probably ending up with 20 million tokens or something like that. That's very small in general compared to the billions of tokens that go into training the base model.
Yeah, PaLM is a trillion-ish tokens, right? I mean, the original PaLM, if I recall correctly, is order magnitude trillion.
That's right. So I think the paper, they say 760 billion, but yeah.
I think one thing to add, because one image will be converted into 256 tokens. So I think the 20 tokens Vivek mentioned is probably only on the text side.
Yeah, roughly somewhere. Yeah, you depending on the exact data, 1 million into 20 or 200, and you get the number of tokens, but it's still fairly small. Then I think in terms of compute, training these models, I would like to think it's more in the 1 to 10% realm of training the base model. One of the factors that come into play over here is also, the more chips that you have access to, and we are training with TPU v4 chips over here, the faster your speed of iterations are as well. And so in that sense, that is maybe something that's disproportionate between the base model and the fine tuning that you can do, in the sense that we may end up, for different reasons, for access of, because say we have access to different kinds of compute, we may end up having a different chip configuration or the number of chips that we end up using. And so that sometimes plays a part, and that in turn also impacts the iteration speed over here. But I think the order of magnitude is roughly between 1 to 10%.
So how fast is that cycle time? I guess I'm interested in that when you're running your 300 experiments. I mean, a 12B model, if I had to guess, I would guess that you have kind of discretionary access to that level of compute and like probably don't need to go, reserving or anything. And I would guess those also return by the time you come back with a new cup of coffee, or is it maybe not quite that fast?
I think on average, it takes a couple of hours to finish training with the 12B model. So it's fairly fast. And sometimes I don't have to run the experiment like to the end to be able to know if I want to make any change.
That completely depends on the number of chips that you have access to. So if you don't have enough number of chips, for example, if you have, say, 1/10 the number of chips, then that 2 hours will become like 2 weeks.
So certainly there's easy knob that we can turn up the data parallelism. So basically running multiple copies on different segments of the entire data set. That's going to give us significant improve in efficiency.
Yeah, this is a good point because I think people are aware of the fact that this is a parallelizable process, but the way you're parallelizing here with data parallelism is you're essentially, while still in the training, I mean, people maybe have a little bit more intuition for this in the inference side of things, but still in the training process, you're basically saying, I'm going to copy the model a number of times. We will run the training process itself in parallel. And then there's, you kind of collect all the gradients and all the adjustments you want to make to the weights. And then you basically just sum those, right? And kind of the next round starts with like the sum of all those gradients found across all the different copies. So that's pretty much, I guess there's maybe some loss of efficiency there in the sense that like, all these different gradients, if you did them sequentially, maybe they would kind of approach the goal a little bit faster. But the dominant effect obviously is that the parallelism speeds, it up roughly speaking by like how many copies you have, I guess, right? If you're going to do now, okay, I've done, a ton of experience. It's time to really start to do the experiments on the big model. Is that like now a few days to run one round of the 562? Like I'm really interested in how fast you can iterate, because that seems like it's going to be a huge driver of how fast you're going to solve all these other little remaining issues that we've been, touching on.
With the compute that we have available, it's on the order of weeks.
It's incredible. Everything is kind of going, exponential at the same time, and just also the iteration cycle dropping to, hours for significant scale experiments, and then weeks for like the full Palm E562B scale. That is, it's probably an underappreciated fact of the entire progress. Is just like you're able to run so many more experiments than people could run a couple of years ago.
But maybe one detail over here is as you scale up these models, the other factor is more often than not, you're not going to be able to fit them onto a single chip. And so there is model parallelism that comes in. And so now you're sharding the different parts of the model across different chips. And then in addition to that, you have data parallelism. So it's like a 3D mesh in many ways. And we like to call that a mesh system over here. And PAX is the framework in which we define the mesh for the model. So that's another factor, because as you're scaling up, the number of chips that you need to like efficiently run these training workloads also increases quite a bit, and that adds in. So we have to take all those factors into account when we are training these systems. But in general, I think you are right that the progress in terms of with the hardware and the frameworks that we have allows us to do things in general more fast than before. But then if you're scaling things up, then that is an effect that is pushing you in the opposite direction. So maybe the speed doesn't change that much, because while you're getting better hardware and software, you're also scaling up these models, and in turn that just increases your training time. I would also add maybe a couple of other things. One is the fact that now I think there is generally going to be a push towards more compute efficient approaches to scaling these models, particularly in the multimodal setting. And so the more we can, for example, make use of specialist encoders that have been really well tuned for tasks, such as the WIT22B that has been trained on I think close to 1 billion images, and craft that into a language model like PaLM that has been trained separately, but again on 1 trillion tokens. And if you can figure out compute efficient ways of doing that crafting process, I think that is going to be incredibly impactful, because in general there's a lot of competition for compute, and the AI is like, such a broad general purpose technology, and you can see so many different safe and beneficial use cases spanning not just biomedicine, but also like energy and climate change and beyond. And so people would want to like make use of these systems, and so that there is in turn like contention for resources. The underlying message is, even at places like Google, efficient approaches will trump out. And so that's something we hope to build, and maybe Tao can say more over here on this.
Yeah, please do. One question I specifically did have on that efficiency point is the approach here is an end-to-end fine-tuning, right? So all 562 billion parameters are subject to change. There's also kind of another class of approaches that seem to have their, I'm sure, pros and cons in all sorts of different, nuanced ways. But from a compute perspective, these kind of like bridge or adapter structures are also often like quite effective. So, did you guys consider doing something like that, where you'd say, hey, instead of messing with all 562, why don't we just insert another 10B at the end and kind of do the last kind of adaptation of the weights or whatever? I mean, so obviously simplifying there. We've seen a lot of those things work. So did you consider an approach like that?
So we actually tried, even in our end-to-end fine-tuning, where you can freeze the language model and only tune the vision, or do only freeze the vision and tune the language model, or freeze both vision and language model and only tune the alignment layer. So there are different choices. I think I ran some experiments when I freeze the language model and only tune the vision and alignment. And I think what I've seen preliminary evidence is, I think the convergence rate is slower. So it takes longer time for the model to reach the performance that I get when I fully fine-tune everything.
But it does generally kind of work.
Yeah, I think in the PaLM-E paper, they also did the frozen language model version. I think this is also some experience that we have gained over the development of Med-PaLM. For Med-PaLM 1, we did prompt tuning, which is a efficient parameter and data efficient tuning methods. And then for PaLM-2, we did the full end-to-end fine-tuning. So I think the evidence that we have observed is actually full end-to-end fine-tuning gives you the best performance lift, provided that you have at least a reasonable amount of data.
Yeah, I think that's right. And it's also true even when you compare like low rank approaches such as LoRa for fine-tuning. It turns out that if you can do end-to-end fine-tuning without using LoRa with the same data, then I think convergence is faster, and the model quality also turns out to be generally faster. That's our empirical evidence at this point of time. So even though like people like to say LoRa is like, for example, more compute efficient, like in terms of like the number of cycles that you spend optimizing with that approach versus say an end-to-end fine-tuning approach, it may turn out that the compute is actually kind of the same.
The other thing that jumped out to me is, if I understand correctly, this is the original PaLM that this is based on, right? As opposed to PaLM-2. I guess if I had to guess, that's maybe just a function of the fact that PaLM-E was based on PaLM, and so you're kind of building on. But there's a couple of different tracks here, right? Is the next? I'm going to go ahead and title your next paper now, Multi-modal Med-PaLM 2. So when can I expect that one to be dropping?
Yeah, so based on the learnings that we had from the Med-PaLM paper, I think we are exploring different approaches where we can achieve the same journalist biomedical AI. I think one example is what Vivek had said. We take a more modular approach. We have these modality-specific encoders that might be small, like a CNN ResNet, and then we find ways to combine them with a shared language model. And we can take any state-of-the-art language models that we have and potentially get even like better performance in terms of, for example, instruction following, and also augment the language model component with stronger conversational capability. So we might be able to unlock new capabilities for this biomedical journalist AI system.
So maybe in addition to that, like I think the architectural details, there's definitely a lot of low-hanging fruits in terms of how we approach the training, as well as the components that we're using to architect the overall system. But then the other question is also in general around utility and what capabilities that you're targeting with this generalist system. And so we're also broadly thinking about that. And so in that sense, we would want to have the next version of the system not only be, better than what we have today on the multi-med bench of tasks, but we want to expand that bench of tasks that we are considering to maybe include more different kinds of medical imagery, or more biomedical data, such as data from different kinds of genomic sequences like proteomics. And so there's so much rich variety of data and tasks that we can start bringing into this system. And then again, the approaches are also there's, I think, a range of approaches ranging from tool use to adapter or grafting or bridge approaches to training these generalist agents with like end-to-end fine-tuning. And so the opportunity is there, but I think ultimately it comes down to what problem are you solving with these systems. And I think that's the root problem that we, or the root question that we first ask before we embark on these giant model training runs or these giant projects.
It seems like it's basically, can we create an AI doctor? I mean, is it as simple as that, or how would you frame the motivation for the next system at this point?
It's no longer science fiction to think that that is possible. I would still say that we are very, very early, not just in terms of, the technical development, like architecting the system and the model as a whole, but definitely in terms of like validating these solutions, verifying them, trialing them in, real world settings. But for me, the most exciting part is it feels like that is all eminently possible and doable. And that all seems science fiction maybe even just a few months back, but now I think that's all possible within a very reasonable time frame. And so I think that is the most exciting aspect. And maybe one of the other things is, again, like doctors today do a lot of different things, and hopefully we'll be able to build AI systems that can be effective teammates for them, effective assistants for them, like mimic a lot of the tasks that they do and take a lot of their burden off them, like the administrative tasks and everything. But then the other impressive thing is, for example, these models can start doing things that maybe clinicians are not trained to do. Like clinicians are not trained to interpret genomic data, for example, but the scale at which we are able to measure fundamental genomic data from individuals at scale today, that the cost of it is going down even faster than Moore's law. And so that is going to be a signal that we want to be able to repeatedly tap into in the future. And so we can have these AI systems in some ways actually be better than, say, human doctors today on that front, like new modalities of data, new signals that we are going to be able to measure with a high degree of precision. These models are going to be able to make sense of that. And so that in some ways that's actually superhuman capacity to provide care. And then maybe the last thing I would say is also, as you start training these systems at scale with such diverse biomedical data, the hope is in the process of doing that, you're going to be able to also fundamentally transform your understanding of human biology, of disease mechanisms, of disease trajectories, and hopefully that'll lead to new insights such as potential new biomarkers, or different causative gene variants for, say, certain diseases that have been long-standing grand challenges, or designing of new therapies. And so in some ways you're also building out like an AI biomedical research scientist, or like a research assistant or something like that. And so the nice thing is, I think the base components of these systems, they kind of lead to all these different applications. And so I feel like that is the most exciting aspect over here.
One of the things that really jumps out in the paper is this notion of emergent capabilities. I'd love to just hear your comments on emergent capabilities. I also want to hear a little bit about kind of the next generation of validation, because you guys have done a lot of work through multiple papers on creating these benchmarks and being very systematic. But it seems like maybe not quite yet with this one, but probably the next one. I'm wondering, at what point does it go to more of a clinical trial type of modality as well, where you'd say, look, I mean, we can characterize this thing 100 ways, but at some point it is time, right, to be like, let's give it to people and see if they end up healthier, than they were if they didn't have it. And that seems like that time has got to be close at hand. So emergent capabilities, and then kind of actual field clinical trial style validation.
Yeah, I think Tao and we had a lot of debate about using the word emergent capabilities in the paper, just given the wider debate in the community with the Mirage paper, for example, coming out. I don't know if Tao, you disagree with this. For me, emergent capabilities are just something that you did not predict would happen or exist in the model that you're building. It's maybe less about model scales per se, or whether there's a continuous or a discontinuous improvement in performance on some of these tasks or capabilities that you're looking at, but more about what unexpected new things are you seeing over here. And so maybe Tao can talk more about the TB example that we had in the paper.
I think one interesting finding that we had from this generalist model is when the model was trained on chest X-ray images and with 14 prevalent clinical observations, such as the enlargement of heart. But it's not, so TB is not pathology label that we specifically trained the model on. But when we present another chest X-ray image, which is acquired from a different center, and the major pathology is the TB, and then we prompt the model asking if there's any abnormality in the image, and ask the model to generate explanations. So in this case, describe the findings in the image. The model was able to actually characterize the correct lesion type, which is cavitary lesion for tuberculosis particularly, and also be able to identify the correct location in the image where the lesion is. But we also showed the caveats of the model, because the model cannot really characterize every single lesions in the image. There might be some omissions, but we are excited that the model can actually identify the correct location of TB and also the right lesion type. I think that's the benefit of the model probably have seen like literature on the TB, and now it was able to generate reasonings conditioned on the visual input.
Maybe I'll quickly add a couple more things. One is I think we showed this in the paper as well, is the number of examples that you need to actually teach the model the concept of TB. We show that that's actually 0 for us, because we're just able to like provide a language description of it. And so I think that is again coming down to the power of language, where you mapping everything to language means you can start describing, you know, signals and other modalities, information and other modalities just through language. And, you know, that really helps a lot with this kind of few shot learning. Maybe the other quick detail I'll point out is this definitely seems to be like an emergent capability, because when we looked at the 8B model, that was not capable of providing any sort of explanation or description over here. But as soon as you start, you know, having a model that has more capacity to do nuanced language reasoning, and so both with the 64B and the 562B model that we have, we see the ability to not only like, you know, make predictions about the presence or absence of TB in image, but also actually describe it to a degree that a radiologist would say is fairly accurate.
So let me unpack how that works as I understand it. And you tell me if I am getting anything wrong here. The finding is you had 14 different types of radiology images that were used in training.
Basically, for each image, there might be 14 different pathology labels, different conditions that you might find in the chest X-ray. That's the prevalent ones and of clinical significance.
There's 14 labels on the images that you're using in the training. Tuberculosis is not one of them. But you find that nevertheless, when presented with an image showing tuberculosis in the chest X-ray, the overall system can identify that. And not only that, but can identify the specific location in the image where it is found. So that's pretty amazing. You know, emergent capability per your definition of things you didn't predict. And I guess what's happening there is the language portion of the model understands, you know, has enough information about tuberculosis such that it is able to effectively interpret the image as it is projected into language space in the form of 256 tokens. I'm always fascinated by the fact that these projections end up in a place in language space that no actual language can access. But it must, you know, it is obviously communicating or, you know, transmitting information about like what is seen where, in a way that, you know, it's also interesting to notice, you know, picture's worth 1,000 words. Here we've managed it with 256 tokens. Enough information is there, and there's enough understanding of that information. So essentially, it's kind of like the image portion is to the language, because it's in this language space, right? I almost imagine it like, I don't like to anthropomorphize too much, but it's almost like it's whispering into the language part's ear, you know, in this, you know, portion you see this thing, and in this portion you see this thing, and all this kind of just visual data somehow in language space is enough. And then the model from there can kind of take it and be like, all right, well, if you're telling me that, then that sounds like tuberculosis. I mean, that really is pretty incredible. And I have to say, the labeling that an emergent capability seems very reasonable to me. I don't know what else you'd really be looking for if you know, what, I mean, tell me, I guess What's the debate on that? What's the case that is not an emergent capability, or that term is, maybe it's just that the term is more trouble than it's worth?
Yeah, I personally, I just think that's a buzz, like word.
So what would you say? I mean, or how do you think about is that a surprise to you when you found this result? Were you guys surprised by it?
So I am not surprised by the model was able to identify TB, even though it's a chest X-ray image that is acquired from a different center. It's still chest X-ray. So somehow I think this image is still in distribution, even though it's a completely different medical concept. I think I would be rather excited if actually we are doing the additional analysis, for example, presenting the model with the founder's image. That was not looking closely like any of the images that we put in the training, and see if the model can actually characterize the image purely based on the language knowledge that it has accumulated during training. I have high expectations, so I want this to be as good as possible.
Yeah, maybe just quickly summarizing that. I think what we have shown so far is interpolation within the distribution of what models trained. And a lot of people still like to call that as creativity or intelligence. I know that Demis Hassabis likes to call that level 1 of creativity or intelligence. But I think what Tao is saying is he's more excited or interested to see if the model can extrapolate outside of the space of distribution that it's trained on. And so once you start giving it out of distribution examples, like a fundus image, for example, can it still start doing these novel multimodal reasoning in that space? The early evidence, I would say, is promising, but I think we still have ways to go over there. So hopefully more soon.
So then going back to the clinical trial concept for a second, how close do you guys think you are to running not a sort of task level evaluation, but a more kind of system level evaluation?
Definitely not just us within this room over here in this virtual room for this podcast who are well placed to answer that. But also us just within at Google are probably also not well placed to answer that. I think that's actually a broader question around how we regulate these more generally capable AI systems, because the way in which we typically regulate AI systems as medical devices, as software as a medical device, is we assume that they're only good at certain tasks. So they are these supervised systems that, for example, can only do this one task, and that we know the bounds of their capabilities, but that also allows us to put numbers around their effectiveness and verify and validate them appropriately. But then as soon as you have these generally capable systems, then the interactions that you can have with that system just explodes, and we don't have a reasonable method, or you can't basically retrofit the framework that you had for regulating, say, supervised classification systems or single task systems into this framework of generally capable AI systems. And so that doesn't exist today, and I think that needs to come into the picture. And so it's a conversation that's ongoing with people who have broad regulatory expertise, say with the FDA, with EU, and different parts of the world. But as things stand today, we do not have that. I think what you suggest is actually a very reasonable approach to take. And maybe that is the approach that we go down the route of, where, for example, we give a generally capable system such as Med-PaLM-2 to a doctor, or put it in the hands of people, and then we run a controlled trial and look at health outcomes, say after 6 months, a year, and see if people are just more healthy and feel better about themselves and beyond. And maybe that's the way to go over here. But right now, as things stand, that's not how we are supposed to be regulating these AI systems, because the FDA definition of what an AI system no longer fits with what we are building today.
So do you think that you're blocked by current regulation from doing something like that? Or is it more that not you obviously, but Google as an institution wants to make sure that it has a regulatory regime to fit into? Because you could imagine one attitude might be, hey, there's no specific law against this, we're going to try and do it. But another might be we want to make sure that there's a law that says how to do it before we do it.
With Med-PaLM-2, we are rolling out the model first to trust it, test users to gather feedback that can in turn inform our model development to make it more safer and effective. So I would say it's evolving. We are also learning, navigating along the way.
What happens if you ask it questions that are not at all about medicine, or about something that's I imagine, in the mature version, you would want it to refuse to be your lawyer, right? You would want it to refuse to do all sorts of things that are not kind of in its wheelhouse. Is that an aspect that you have developed at this point? Or is that just kind of like left for future work?
I think that's a question general to all the like AI systems, even the general purpose language models, how to put guardrails around its response. In Med-PaLM2 testing, we actually presented the model with a set of adversarial questions that with the intention to break Med-PaLM2. So there's a lot of work that's needed in order to basically put these different guardrails around the model so it doesn't generate bias response or even amplify the health inequality that was present in the training data.
Yeah, and maybe a couple of just broader points. One is the safety and alignment question. That's very important for the generally capable agents and systems that we are building today. But I think one of the nice things about working in a domain such as biomedicine, where, for example, maybe you're building a bot for primary care triage, or bot that helps with chronic care management, the domain is constrained, and that in turn makes the safety problem and alignment problem more tractable, say compared to a general purpose chatbot such as GPT-4 or bot that is supposed to talk to you about philosophy or music or poetry or whatever. And so just because of the broad range of capabilities and the domain being unrestricted, it becomes a lot more challenging. Whereas for us, I think there are approaches that will be intractable for safety and alignment if you had a general purpose chatbot that become a lot more viable once you have like constraints over here. So I think that is going to be one direction that we are going to take technically to do more safety and alignment stuff, where the work that we do over here is going to be very domain specific, but that in turn will allow us to proceed with guarantees around these systems and enable more of these clinical trials and regulatory conversations with safety as front and center. Coming back to the other question that you had, are we blocked by regulation? I would say a couple more things. I think it's not necessarily true. I think there's still a lot of work still to be done on the base model capabilities and on safety and alignment of these systems, and that can happen in parallel to the question around how we regulate these systems. And then the other thing is, it's just such a transformative technology, such a pivotal moment in history, as you mentioned in the beginning of the conversation, that I think it's okay for us as a society to take time and have deliberate conversations, thoughtful conversations before we come to a conclusion one way or another on how we use these technologies. And so in that sense, I think it's more important for us to get this right rather than just being fast over here, and hopefully that happens with a degree of urgency given all the potential.
You had mentioned, a kind of deep personal motivation around having grown up in a place in, a poor part of the world in India where access to medical care is just not, what obviously you would hope it would be. How far do you think we are from really changing that in a fundamental way? I mean, you said it's a transformative technology, but it seems to me like we're not many years away from just radically democratizing access to quality medical advice, if not care. But advice is often worth a lot, as a precursor to care. So, I mean, you said it's not science fiction. Like, are we really looking at like a 3 to 5 year time frame to put a genuine AI doctor into everybody's hands around the world?
So for me personally, right, I think, I grew up in, parts of the world where, for most people going to see a doctor was simply not a possibility. Oftentimes it meant walking 30, 40 miles in extreme heat, giving up a day's wages, going without food. And as such, I knew many people who did not see a doctor in their entire lifetimes. And that meant, like, for example, not detecting diseases earlier, or, dealing with the burden of like chronic diseases and overall like lower life expectancy and quality of life. And for me personally, I've always wanted to do something about this. This goes back a decade now in terms of like the motivation of doing something about democratizing access to high quality healthcare. I'm pleased to say that I think the arc of progress in technology and AI in particular, especially in the last couple of years, allows us to dream of that future where world class healthcare is democratized to billions of people worldwide, and we put a world class AI doctor directly accessible in the pocket of billions of people worldwide. So in that sense, I think AI is truly transformative, because I don't think there's another industry where the biggest problems of that industry are immediately solvable by AI today. For example, the biggest problems in healthcare are A, access to healthcare, B, cost, and C, quality. And all these things can be radically improved by AI today. And so I think that is immensely exciting for all of us working in this field, because we see this opportunity. And that is not just true for like places like India or Africa, for example, but also like, solving there are different challenges in places like the UK and EU and the US. But again, all those problems can be solved by AI today. That just feels like, the opportunity of a lifetime and that just excites me and Tao and all of us who are working on this, not just at Google, but in the wider space at large.
Tao, any other closing thoughts you want to share?
I want to share like my personal motivation. Of course, I share what Vivek said, to make the medical care accessible to billions of lives. But coming from a neuroscience background, I have always been intrigued by exploring the mutual benefits between AI and human intelligence. I think that's what got me excited working at Google, and especially working on this medical assistant job, because I think it empowered me to do the things that I have dreamed of, which is that I want to use AI to accelerate scientific discovery. This multimodal Med-PaLM is providing tools for us to tackle problems like that. We can leverage the language capacities, like the language model has seen all the, let's say, PubMed articles, all the biomedical research. And if we can leverage that knowledge and help us to discover, let's say, new genetic biomarkers for Alzheimer's or Parkinson's, that would be awesome.
Yeah, it's a huge vision. At some point, it starts to seem like even the AI doctor in your pocket is maybe too small of a vision relative to the potential. So it's good to point out that it's not just operationalizing and scaling what we can do, but it's also kind of changing what we can do. Super fascinating to learn all about this new system. And I hope we can do it again in a few months when Multimodal Med-PaLM 2 comes out, or whatever the next big milestone is, because you guys are certainly on a roll. And I think it's one of the most consequential efforts going on in the space today. So in conclusion, Vivek Natarajan, Tao too, thank you for being part of the cognitive revolution.
Yeah, thank you so much for providing us the platform to talk about our work and also sharing more of our vision.
Yeah, thank you, Nathan. We really enjoyed the conversation.
It is both energizing and enlightening to hear why people listen and learn what they value about the show. So please, don't hesitate to reach out via email at tcr@turpentine.co, or you can DM me on the social media platform of your choice.
Omneky uses generative AI to enable you to launch hundreds of thousands of ad iterations that actually work, customized across all platforms with a click of a button. I believe in Omneky so much that I invested in it, and I recommend you use it too. Use CogRev to get a 10% discount.